In this video, we're going to talk about Newton's second law in the radial direction. So let's say we have a net force acting inward when we are moving in a circle. This is not a new force. This is called our centripetal force, and it is always going to be pointing to the center of our loop. Let's examine first the bottom of the loop. Let's say we have a mass at this point. At this point, we have a normal force that is acting upward, and we have a downward force that is our force of gravity equal to weight. So where is the direction of our radial direction? That is going to be up, because the center of the circle is upwards. So now, if we write the Newton's second law for this position, we are currently looking at the summation of forces equals to our mass times acceleration. We have normal force pointing upwards, and we have weight force pointing down. That's equal to our mass. And then we are going to have v squared over r. Acceleration in the centripetal direction is equal to v squared over r, which is why we were able to plug this in. And again, we have our upward direction as positive. So if we solve for our normal force here, this is going to be adding mg to both sides. We get m v squared over r plus mg is equal to the normal force that is acting at this position where the block is at the bottom point of the curve. In this bottom position, we have a normal force that is going to be greater than weight, and what that means is you feel heavier at the bottom. What about when you're at the top of the loop? If you're at the top of the loop, you are currently upside down. So you're going to have a net force that is perpendicular to the point of contact of the surface, pointing downward. This is your normal force. You also are going to have your weight force acting down, since your gravity always is acting down no matter where you are on Earth. Now, where is our radial direction going to point? It's still going to point in the center, because our center is in the downward direction this time. So if we apply the Newton's second law here, we have the summation of our forces is equal to mass times acceleration. We have normal force and mg acting in the same direction. So this time we're going to add them, because in this case, we are going to have our AC acting in this direction, just as we had our AC acting in this direction. So we are going to say that our direction of AC is what we're going to consider our positive direction. Therefore, this would be positive in the eyes of the top, and then in the eyes of the bottom, this would be positive. Now, this is equal to our mass velocity squared over r. Next, we just solve for normal force, giving us this expression here. In this case, we see that our normal force is less than weight, which is why you feel lighter when you are at the top. Now, you're going to have a special case when you are at the top. Now, if our normal force is equal to 0 at the top point where we're upside down, then we have our weight is equal to our Fc, giving us mg is equal to mv squared over r. We can cancel m. We get g is equal to v squared over r. We multiply both sides by r. We get v squared is equal to r times g. We take the root of both sides, and v is equal to the root of r times g. And this is how we derive our minimum speed to stay on track. So overall, when you're at the bottom, we end up with normal force is equal to mv squared plus mg, where mv squared is divided by r, by the way. and you feel heavier here. At the top, you have normal force is equal to mv squared over r minus mg, and you feel lighter. The reason is for when we're at the top, we have our gravity is already pointing towards the center, so our normal force does less. However, bottom, our force of gravity is going to pull away from our center. So here, our normal force does less.